Okay, so now we will start one more important physical chemistry chapter, electrochemistry. This is very important and here physical chemistry. It is also weightage chapter. Mostly will get the questions from the mains for mains and advanced from the electrochemistry. We'll start here electrochemistry. And what is this electrochemistry? What it deals actually? We can see the word electrochemistry. You can see two terms here. One indicates the electro, or nothing but related to electron, and the second one chemistry, related to the chemical reactions. Mainly here electrochemistry deals with the interrelation between the electrons, nothing but electrical energy, and chemistry, nothing but chemical reactions. So it is the interrelation between the chemical energy and electrical energy, means conversion of one to other. Conversion of electrical energy into chemical reactions and chemical reactions into electrical energy. So some chemical reactions spontaneously they can undergo and they can produce the electrical energy, and by applying some electrical energy on chemical reactions while undergoing spontaneous reaction, and they can convert the electrical energy into the chemical reactions. That overall conversion one to other, electrical energy to the chemical and chemical energy into the electrical energy, that mainly we will discuss in the electrochemistry. And this electrochemistry we can deal in three parts. In that, the first one, electrochemical cells, or mainly here galvanic cells, and the second one electrolytic cell, and the third one in terms of electrolytic conductance. See here we discussed that electrochemistry interrelation, conversion one to other. So to convert one energy into the other energy, we required some devices. So here the device which converts chemical energy into electrical energy is called electrochemical cell or simply galvanic cell. Here it converts chemical energy into the electrical energy. The cell which converts chemical energy to spontaneous reaction is called electrical energy. And electrolytic cell, and this is the device or the cell which converts electrical energy into chemical energy. Electrical energy to chemical energy means to occur a chemical reaction spontaneously, we will apply some external energy here. Electrical energy to the chemical energy is called electrolytic cell. Conductance, here we will discuss the electrolytic conductance of the substance. So these three. So we will take up one by one here. First we will start with electrochemical cells or galvanic cell. So first part here, first part of electrochemistry, electrochemical cells. So these are the cells which converts chemical energy into electrical energy. Best example, galvanic cell or Daniell cell. And the reactions involved in electrochemical cell is the redox reactions, and they are the spontaneous in nature. Anyhow, before we enter into these electrochemical cells, we will discuss some basic terms involved in the electrochemical cell. That one, first of all, electrode. What is the electrode here? Electrode is a metal rod. Most of the cases will take metal, sometimes non-metal, which is dipped in its own ionic solution. It is a metal rod. Which is dipped. in its own electrolytic solution. The metal rod which is dipped in its own electrolytic solution is called electrode. So, which allows the passage of current and its conductance. And here we have two types of electrodes. Mainly in electrochemistry we will use two electrodes, one is the anode and cathode. And two types of electrodes, one is anode and other one is cathode. Generally, which one we take as anode? So, where the oxidation reaction takes place, the electrode at which oxidation takes place. It is the electrode where oxidation takes place. Is anode. Quite opposite, this is the electrode where reduction reactions takes place. So, always at anode oxidation and always at cathode reduction. Whatever the type of cell it is, whether it is a electrochemical cell or electrolytic cell, always anode oxidation, cathode reduction. Generally, anode is the negative part in case of electrochemical cell or galvanic cell. The sign of the anode, but this is the positive electrode in case of electrolytic cell. In electrochemical cell, this is a negative, and in electrolytic cell, it is a positive. And similarly, here cathode, in case of galvanic cell, this is a positive electrode. And the negative in case of electrolytic cell. And one more important point here, always electrons will flow from anode to cathode, both the cells. Electrons flow from anode to cathode, then current always flows opposite to the electron flow, then current flow from cathode to anode. This is our electrode. Next, one more term here, electrode potential. Electrode potential. Generally, this electrode potential will represent with the symbol E. Electrode potential means it is a tendency of an electrode to gain or lose electrons. It is a tendency of an electrode. To lose or gain electrons when dipped in its own solution. When it is in contact with its own electrolytic solution. That is called electrode potential. Again, lose of electrons or gain of electrons. If electrode gains electrons, we can say that is a reduction process. If electron loses electrons, we can say it is oxidation process. So here potential. So accordingly we can take two types of potentials here. One is oxidation potential and one is the reduction potential. If the electrode loses electrons, then we can say it is oxidation potential. If the electrode gains electrons, we can say it is reduction potential. Again we have in its own electrolytic solution. Okay, again we have two types of electrode potential in here. One is oxidation potential and the second one reduction potential. Oxidation potential we can represent like EOX, and the second one reduction potential. And this is E reduction. So let us see here one electrode, a metal rod. Let us take one metal rod. Here I will take zinc. Now this is dipped in its own solution, zinc sulfate, electrolytic solution. In another case, let me take one more electrode. This is copper, which is dipped in its own solution, copper sulfate. So here first one, here zinc, what happens? Zinc releases ions, so it loses electrons and it can form zinc 2 plus and 2 electrons. Zinc rod can dissolve in the zinc sulfate solution, so it can give electron to the solution. So it can give ions to the solution, zinc 2 plus, and releases 2 electrons. In case of copper, copper can here copper 2 plus ions. You can take here. They can absorb electron from the copper rod and they can deposit over the metal rod. So first case, zinc giving electrons, and the second case, copper 2 plus ions gaining electrons. Two types of processes. Simply we can say instead of zinc and copper, some metal M, if it releases electrons when is present in its own solution, it can give like Mn plus and N electrons. And here this copper 2 plus, or you can take metal which is present in the ionic form, you can take electrons and form metal. And here we can say if the metal loses electron, this is the oxidation potential, and here metal gains electron, this is the reduction potential. Actually, what is the potential? What is the potential? When you take a metal rod, simply if I take one metal rod, if you dip it in its own solution, metal can give the electrons or it may gain electrons. For example, it gives electrons, then electrons will be released into the solution and the rod can get positive charge. The rod can acquire between the on the metal rod we can see the positive charge, and the solution now will get the negative charge. Now you can see two opposite charges. Now the potential developed between these two opposite charges is a kind of electric double layer. The potential developed between these two electrical double layer is called electrode potential. So in this case, this electrode giving electron, so we can say it is oxidation potential. Sometimes the electrode may gain electron, then electrode may get negative charge and the solution may get the positive charge. Again you can see there the formation of electrical double layer. Again some potential can develop over there, and that potential we can call reduction potential. In this case it is gaining of electrons and here giving of electrons. So simply we can represent the oxidation potential like this. It is a tendency to lose electrons is the oxidation potential. So the representation for oxidation potential is EOX, or we can represent like this. Here metal is converting into the metal ion M to Mn plus. This is also representation for oxidation potential. Or this reaction also indicates here the potential developed E is the oxidation potential only. If I give E equal to X means what? This is the oxidation potential. And in this case we can represent the reduction potential like E reduction, or here metal ion is converting into the metal form. This is also representation for reduction potential. Representations are very important here. Or if I give an equation like this, Mn plus n electrons giving M, and where the electrode potential E some Y. So with this equation we can say that this E is reduction potential only, even though we didn't mention anything here, there is a reduction or Mn plus M. So normal E indicates it is the reduction potential. And one more important point, for a particular cell or a particular electrode, for a given electrode, the magnitude of oxidation and reduction potentials are same, but they are in opposite sign. For a given electrode, oxidation and reduction potentials are same in magnitude. Same in magnitude, but opposite in sign. And this is also very important statement. Means we can write like this: E oxidation potential is equals to E reduction potential, but they are in opposite in sign. If they give oxidation potential, this you can take the same as reduction potential but opposite sign. There is the electrode potential, both oxidation and reduction potentials. And next one more term here, standard electrode potential. This we will represent with E naught. So E naught indicate the standard electrode potential. So again, if we calculate the electrode potential at standard condition, and that we can say standard electrode potential. Measurement of electrode potential at standard conditions. Mostly as standard conditions we will take temperature is 25 degrees centigrade. There is a 25 degrees temperature and 1 molar concentration. One molar concentration, or if they give the electrolytic solution, 1 molar concentration. If they give the gases, 1 bar pressure. It's called standard electrode potential. Calculation of electrode potential at standard conditions at 25 degrees Celsius, or 1 molar concentration or 1 bar pressure. Again same, standard oxidation potential, standard reduction potential. If we calculate the oxidation potential standard condition and a calculation of oxidation reduction potential at a standard condition. So standard oxidation potential. This we can write as SOP, standard oxidation potential. We can represent like this. Again, E naught of oxidation or E naught of metal can give metal ions. So, these are the representations for standard oxidation potential. Similarly, standard reduction potentials. There is SRP, generally we can say SRP, standard reduction potential. So, that is E naught of reduction, or this is E naught of Mn plus M. So, metal ion to the metal conversion, standard reduction potentials. Same here also, just like for a given electrode, standard oxidation potential and standard reduction potential, they are in opposite in sign, but same magnitude. So, we can take E naught of oxidation potential is equals to minus E naught of reduction potential. These are the electrode potential. Next, cell potential. This is electrode potential, and next cell potential or EMF of a cell. What is the cell potential? Or EMF nothing but electromotive force. Simply we can say EMF. So, what is the cell potential or electromotive force? When you construct a cell by using two off cells or two electrodes, then the potential difference developed between the two electrodes is called electromotive force or cell potential. When a cell is constructed by using the two electrodes, the potential difference between the two electrodes, and also the shell should be not in work. So, when it is in not work, the electrode potential developed between the two electrodes. So, we can define like this in use. This is called cell potential or electromotive force. Then the formula for E cell, electromotive force, EMF, or simply we can say E cell. EMF nothing but E cell, electro cell potential E cell is equals to electrode potential of the cathode. We can write as E cathode, the difference minus anode, and here both the electrode potentials are reduction potentials only, and this is very important. When we take both are reduction potentials, here take reduction potentials only. And if you take one, both are the oxidation potentials, or one is the oxidation and one is the reduction, the formula may change. For example, we know that E oxidation is equals to minus of E reduction. This formula anyhow mostly we will use. We can generate other formulas here. E cell is equals to this electrode potential of cathode, that if you convert into the oxidation potential of cathode, this will become as E oxidation of cathode, but we will take minus here, minus this also if we convert into oxidation potential, E oxidation of the anode. So, minus minus you will get plus here, or this we can write E of oxidation potential of anode minus E of oxidation potential of cathode. The formula will become like this. If you take oxidation potential, then anode minus cathode. If you take reduction potentials, cathode minus anode. and if you take one is oxidation and another one is the reduction. Another formula you can write: E oxidation of anode and this cathode, if you take E reduction potential, then plus E reduction of cathode, because oxidation, if you convert into reduction, minus minus plus. So, E cell equal to oxidation potential of anode and reduction potential of cathode, that also can give the E cell value, cell potential. But mostly you should remember this formula only for calculation. Simply cathode minus anode, the value should be reduction potentials only. And one more point you should remember here, if nothing is mentioned about the reduction potentials or oxidation potential, then you should assume that always electrode potential nothing but it is the reduction electrode potential only. Okay, if it is not mentioned particularly, this is also important point. Then consider that electrode potential as or standard electrode potential, either electrode potential or standard electrode potential as standard reduction potential only. If not mentioned, then you assume that if they give only electrode potential, that nothing but standard electrode potential only. And if they mention specifically oxidation potential, then only you go with that it is oxidation potential. So, till then whether it is electrode or reduction electrode potential, always you have to take as the reduction electrode potential only. This is also very important point. Next, some important points about the factors effects on the cell potential. You can see this one. Factors affecting on cell potential, or you can take electrode potential also, either it is a cell potential or electrode potential. The cell potential or electrode potential is independent. It is independent on a very important stoichiometry. Of electrode or reaction or reactants or products in a chemical reaction. It will not depend on the stoichiometric change. Means if I take one reaction like this, X A gives rise to product where E oxidation, some E potential, electrode potential equal to some N volt. Then if we change this Y A to products, again the electrode potential or cell potential is the same only, N volts only. Whether you change or not, the stoichiometric coefficient will not change the electrode potential or cell potential. This is for same type of electrode or same type of the cell. The second one, it is independent on the amount of solution. Independent on amount of solution. And the third one, it is independent on the thickness of metal. Whatever the way you take the metal, whether you take in the form of wires or rods or sheets, plates, doesn't matter, always the electrode potential is same only. It depends on first one, temperature, if you change the temperature, the cell potential or electrode potential may change. Next, concentration, there is nothing but activity, either concentration or pressure. If it is a solution, is concentration, or for gases it is a pressure. So it depends on concentration of solution and pressure of the gas. And one more, third one, it depends on nature of electrode. Nature of electrode. Different electrodes, they are having different types of electrode potential values. And one more important point here, electrode potential or cell potential, they are intensive in nature, not extensive properties, they are intensive properties. Electrode potential or cell potential, nothing but EMF of a shell. Electrode potential or cell potential is an intensive property. They are not in additive in nature. Extensive and intensive properties we have discussed at the time of thermodynamics. So they are independent on the amount of substance, intensive property. Extensive properties means depends on the amount of substance. So they are not additive in nature. That means not additive in nature. Extensive properties are additive in nature. And this point also very important. Next, spontaneity of a cell. You can take electrode potential or cell construction, whether the cell is spontaneous or not, which case it is a spontaneous. There is a spontaneity of a cell. According to the thermodynamics, we know that electrical work done, there is a non-PV work. Electrical work done or electrical work is equals to charge into potential. Your charge you can take for 1 mole of electrons, a number of moles. The charge of electrons will represent with the Faraday's, and potential nothing but for a cell, that is a cell potential E. And here we have electrical work done according to thermodynamics, delta G. But for a spontaneous cell, delta G should be negative. So delta G equal to minus NFE. Can write delta G is equals to minus NF E cell. This is from thermodynamics, the relation between the Gibbs free energy and cell potential. from the spontaneous or non-spontaneous. First case for spontaneous process. So, if delta G equal to minus NF E cell, we can write delta G naught. This is a standard value. Gibbs free energy, standard Gibbs free energy. Delta G equal to G naught equal to, you can write minus NF. Again, standard E cell minus NF E naught. So, for a spontaneous process, always delta G should be less than 0 or negative. We know that delta G equal to minus NF E cell. So, you should get delta G equal to less than delta G is less than 0 for a spontaneous cell. Then that is possible when anyhow N is number of moles, F is a Faraday E cell. So, if the E cell value is positive, always positive, then the delta G value will get negative. Then for a spontaneous process, delta G less than 0, but E cell should be greater than 0, means E cell should be always positive for a spontaneous cell. A spontaneous chemical reaction, or instead for a spontaneous chemical reaction, E cell value should be always positive. Next, for non-spontaneous process. We know that delta G is greater than 0 or positive, and when it is positive, anyhow this is negative NF, and if you take E cell is always negative, then delta G value will get positive. So, in that case E cell should be less than 0 or always negative. The third condition for equilibrium reactions. In case of equilibrium, delta G should be equal to 0. Then if delta equal to 0, ultimately E cell also should be equal to 0. And one more important point here, for equilibrium reaction, delta G equal to 0, but delta G may or may not be equal to 0. This is not equal to 0, means E naught cell is not equal to 0 at equilibrium condition. Only E cell equal to 0 at equilibrium condition. This is also very important. We will use this for further calculations. At equilibrium condition, the difference between the E cell and E naught cell. This is about the spontaneity of a cell.